Welcome to Lecture Online, and here's another example of how to work with simple harmonic motion in physics. Here we have a little example where we have a toy car that's hanging from a spring. The toy car has a mass of 0.15 kilograms. The spring constant is 300 newtons per meter. And let's say that it's oscillating up and down. The equilibrium point is right here. And at this very moment, the position away from the equilibrium point is 0.012 meters, which is 1.2 centimeters. And they're asking the following questions. What is the total energy? What is the maximum amplitude? And what is the maximum velocity while it's oscillating back and forth? And at this position right now, the velocity at this moment in time, when it's this far away from the equilibrium point, is 0.3 meters per second. So, starting out with the question, what is the total energy? We can say that energy total is equal to the potential energy that it has plus the kinetic energy that it has. So let's see if we have the information. Potential energy is defined as 1/2 kx squared, and the kinetic energy is defined as 1/2 mv squared. And we do indeed have the k, we have the x, we have the m, and we have the v, so we have everything we need to find the total energy. So this is equal to 1/2 times k, which is 300 newtons per meter, times x squared. X is 0.012 meters, and we have to square that, plus 1/2 times the mass, which is 0.150 kilograms, times the velocity squared, and the velocity is 0.3 meters per second, and we have to square that. All right, so let's figure out what each of the individual energies are. So first of all, starting with kinetic energy, potential energy, that's 300 times 0.5 times 0.012 squared equals, and so this is 0.0216. The units would be joules, and we'll check that out in just a moment to see if that's correct, plus, now let's take that part right there, so we have 0.3 squared times 0.15 and times 0.5 equals, and that would be plus 0.00675 joules. So let's quickly check our units. So we have newtons per meter times meter squared, and of course this meter cancels out that meter, which is Newton meters, and by definition that is indeed joules. So we have joules for here. How about this one right there? So we have kilograms meters squared per second squared. Okay, let me rewrite that as a kilogram meters per second times meters, because kilograms meters per second, by definition, that is second squared, that is newtons. So this gives me newtons times meters, which also gives me joules. So units seem to check out. So the total energy then needs to be added together, and so this is 0.0216 plus 0.00675, and so that is 5318200 point, and that would be, and that of course joules. So that would be the total energy of the system at the moment we're in this position. Now of course we know that that doesn't change. That would be the total energy anywhere along the oscillatory motion. Now, second part is, what is the maximum amplitude? So the maximum amplitude can be found in various ways, but one way is to say that the energy total, or I'll tell you what, we can probably use the energy equation and say that the velocity is equal to the square root of k over m times a squared minus x squared. And since I know v, I know k, I know m, and now I know x, I can actually solve that equation for a squared. So we can say that v squared is equal to k over m times a squared minus x squared. So then we can say that v squared times m over k, by putting m over there and k down here, is equal to a squared minus x squared. And so finally, I can say that a squared is equal to v squared m over k plus x squared, by moving the x squared term over to the other side of the equation and flipping it around. And then finally, we can take the square root of both sides, like so, and that allows me to find the amplitude. So notice that we can use that very same equation that was derived from the energy equation in terms of velocity to find any variable that we want. So plugging in the numbers, what do we get? Amplitude is equal to the square root of v squared. Now v is at that moment 0.3 meters per second, and we have to square that, times the mass, which is 0.150 kilograms, divided by K, which is 300 newtons per meter. And then we add to that the distance that we're at right now, so 0.012, and that would be meters, and we have to square that. And let's see what we get. So 0.3, we square that, times 0.15, divided by 300, and we add to that 0.012 squared, and then we take the square root of that, and we have amplitude is equal to 0.0137 meters. So just slightly more than what we're at over here during this oscillatory motion. So that is the maximum amplitude that the object will have. And finally, what is its maximum velocity? Well, now that we have the maximum amplitude, we can then plug this back into over here and let x equal 0. Because for part C, the velocity max will occur when x is equal to 0, when it's at the equilibrium point. So velocity when x equals 0 is equal to the square root of k over m times a squared minus 0 squared. I'll just plug that in there so you can see. So now we plug in all the other values. So this is equal to the square root of k, which was 300 newtons per meter, divided by the mass, which is 0.150 kilograms. And then we multiply that times the maximum amplitude, 0.0137 meters squared. So we take what we have, we square that, then we multiply that times 300. We divide that by 0.15, and then we take the square root of that. And the maximum velocity would be 0.615 meters per second. All right, so there you can see that using the very same energy equation, we can find the total energy. We can use that very same equation, turn into velocity in terms of x to find the amplitude, and then by plugging in the various numbers, we can find the velocity anywhere along the motion. And that's how you do a problem like that.